Okay, let's introduce the Laplace transform. Now, we did some motivating examples and reasons why we might care about this in the last video, but in this one, we're going to go back to that summary, and I will write it in blue to be similar. For what are we doing when we introduce this Laplace transform? We are curious on how we can use an integral to see or compare how similar our function is with e to the st. Okay, we are really curious about comparing functions to this very, very common thing that pops up when we solve differential equations. And to do that, we're going to use this a modification of this Laplace transform. So this actually is the Laplace transform on a function right now, but this is over t from negative infinity to infinity. We really are only going to care about non-negative t's in this class, so we're going to use those limits of integration for our Laplace transform. So we'll introduce it a little bit more formally here, and specifically the Laplace transform y of the function little y, we'll say little y is a function. The Laplace transform capital Y of the function little y is given by capital Y of s. So it's being applied to little y. If you wanted to think of it, you could have a subscript here for whatever your little y is. But it's a function of s. It takes a function of t, and it turns it into a function of s. And specifically what that function is going to be the integral from 0 to infinity of y of t times e to the negative st dt, right? We're comparing it to e to the st, and we do that by multiplying by e to the negative st. Again, with the idea that if this integral is big, they are similar. If this integral is small, they are not similar. And of course, one of the biggest this can be is when y is e to the st, because then these cancel out to 1. We have area under the curve of 1 on an infinite domain is huge. Okay, so that's going to be our Laplace transform. And again, we're only worrying from 0 to infinity because that's what t's we're going to be working on. So a couple of comments here, right? Notice that this transforms y of t, right? T was our variable, and now s is our variable. Our independent variables are changing. So that's a big part of the Laplace transform. And then, again, something that we are going to require here, and we'll talk more about this later, is we need y to not grow too fast. We'll say y has to be limited to exponential growth in this. And then specifically, something that I really need to include here is that this is only going to be defined for all numbers s, and they're going to be real numbers s. Because remember, we split up that exponent into the real part and the complex part. The complex part was just for Fourier transforms. So this function is only going to be defined for when this integral converges. So if you remember looking at improper integrals in like a Calc 2 class, we're going to use limits, and we're going to have to make sure that these integrals converge, and we're going to find out what values of s make these integrals converge, and that's where some of those restrictions are going to come into play. So, enough definitions. What does the Laplace transform of a function actually look like? Well, let's do it. So we're going to do an example together. So we're going to find the Laplace transform, which will be a function of a new variable s, for the function y of t equals negative e to the 2t. Going back, what is the Laplace transform doing? It's using an integral to compare how similar our given function is with e to the st. So my question for you is, how similar is this to e to the st? And this is going to be a function of s. So how similar it is going to change depending on what s is. Well, I think there's some values of s that might make this pretty darn similar. Right? If s is 2, for example, it doesn't get any more similar than this. So we should expect y of s, specifically y of 2, to be huge. Okay? And then the further away s is from 2, because again, we're comparing these two functions. The further s is from 2, we should expect the Laplace transform to get smaller. So y of s should be small when s is far from 2. That's what we'd expect. Because again, we're always thinking about the Laplace transform conceptually as this, comparing how similar our function is with e to the st. And it'll depend on what that s is. All right, so we know we have an expectation for what our Laplace transform should be. It should be huge when s is 2, and it should be small when s is far away from 2. Let's calculate it using the definition. So we know that the Laplace transform of s for this function is going to be the integral from 0 to infinity. Remember, we're using this. Our function here is e to the 2t, and this will always be e to the negative st. So all we have to do is evaluate this integral. And y'all are going to hate this, I know it, but this is an improper integral, so we really need to use limits when we evaluate it. But before we evaluate it and before we have to write limit 5 million times, we can simplify the inside a little bit more. This is 2t minus st. Or if you want to, you can make this look even a little nicer, right? Just take out the t. All right, this is just 2 minus s times t like so. That'll make it a little easier to integrate. And remember, s is a variable. It's our independent variable. But in terms of the integral, s is a constant. So it really depends on what we're talking about for whether s is a variable or a constant. It is our independent variable for our Laplace transform, but in the context of evaluating an integral, it's a constant, and t is our variable of integration. That's why this dt really matters. It tells us what we can treat as a constant and what we need to integrate. So in order to carry out this integral, we do need a limit. This is the limit as b goes to infinity of the integral from 0 to b of e to the 2 minus s times t dt. And you do have to write this every single time, because if you don't write this, then the two things are not equal to each other anymore. Now, if you really, really hate writing it, you can go off to the side and just simplify this. And that can be a good strategy if you just really hate writing it. I'll show that strategy. Right? We can. I'll show it in a future video. In this one, let's just be consistent and professional. So this limit, what is this? Well, we have to evaluate this definite integral. This definite integral is just 1 over 2 minus s times e to the 2 minus s times t, right? Integrals of exponential functions are pretty easy. Evaluated between 0 and b. And that's just going to be pretty easy. The 1 over 2 minus s comes out in front of the limit. As b goes to infinity, the inside, we just plug in b. When we plug in b, we're going to get, what are we plugging b into, by the way? T. Okay. And if you ever want, you can always write this on your limits of integration, just to make it really obvious. There's nothing wrong with that. T goes from 0 to b. So plugging in t equaling b is going to be e to the 2 minus s times b, minus when we plug in t equals 0, we get e to the 0, which is 1. Oh, that's nice. So now what is this integral right here? Sorry, what is this limit right here? Well, it depends on what s is. Because if this part right here, the coefficient of b, if this is positive, then we're increasing without bound, we're blowing up. If this is 0, then the limit is just 1. And if this is negative, then the limit is 0. Okay? So many, many things happen. So let's look at this limit. and we're going to change colors really quickly. I'm really trying to model exactly what I said. Let's say I don't want to write all this other stuff. I only care about the green. So we're going to ignore the other stuff for now. And the way that we're going to do that is we're going to go off to the side and say, okay, what is the limit as b goes to infinity of e to the 2 minus s times b? And we're going to find out it really depends. We said that this limit could be infinity, right, if 2 minus s is positive. Because, right, that's just like e to the x. And as x goes to infinity, yeah, it goes to infinity. If s is equal to 2, because really, maybe we could rewrite this if we wanted to. If 2 minus s equals 0, if s is equal to 2, we have e to the 0, which is 1. And if it's negative, e to the negative b will go off to 0. So this limit, this Laplace transform, which depends on s, well, it's going to really depend. So this whole thing, right, green is either going to infinity, 1, or 0. So what do we have? Well, if green is going to infinity, then this whole thing is going to infinity, right? If green is going to infinity, this whole thing is going to infinity. And again, we might have an infinity over infinity case here, but we know s is not 2 for this case. So this is s is strictly less than 2. So we're not going to, we know it's just going to be a number times infinity. We know we'll have infinity. So in this first case, which again, this is s is less than 2, then the integral diverges, which we remember was important because the Laplace transform is only defined for the new variable s that the integral converges. So integral will diverge if s is less than 2. What if s is equal to 2? Then this limit, this green part, is 1. Well, 1 minus 1 is 0, right? And then, so we'll write that down. Right, the 1 minus 1 is 0. If s, uh-oh, wait, hold on. We have a big problem. It's 0 over 0. Isn't it? If s is equal to 2, this part becomes 0. This part becomes divided by 0. All right, so s equals 2, we got some interesting things. We might have to look into that. So far, it's not great. Laplace transform is probably not impressing anyone yet. We got an infinity. We got an indeterminate form. Don't worry, don't worry, don't worry. What if s is bigger than 2? That's this last case. That means the green part 0. We're going to get minus 1 over 2 minus s. And as a quick note, right, minus 1 over 2 minus s, we can just rewrite that as 1 over s minus 2. But I'll write it as the first form for now. Great. How fun. So real quick, is this an indeterminate form that actually is a number, or is this actually undefined? We'd have to use a quick L'Hopital's rule to find this out. But we really should. We should use L'Hopital's rule. We should look into this. All right, what is this? Okay. How do we do this? This is when s approaches 0. We have limits inside of limits. We're going to skip that for now, actually. And we're just going to be a little hand wavy because this is differential equations. And we'll leave more of the precise theory to other things. It turns out that this actually is undefined. The integral does not converge for s equals 2. And we know that for a few different reasons. The easiest way to skip this L'Hopital's rule analysis is just looking at this. And if s is equal to 2, we know it diverges. We just get the integral of 1, it's going to diverge. So if you wanted to skip the work, you can just use that level of analysis, which is formal analysis. It's just a different kind of formal analysis. So What is our Laplace transform? We know that y of s is just, again, I'm going to rewrite this, 1 over s minus 2, but it does require that s is bigger than 2. That's our Laplace transform. Everything else, it's not defined. And we said the Laplace transform is equal to this, but only for the s that have the integral converge. And we said we had this expectation. We expected y of 2 to be huge. And sure enough, yeah, y of 2 is infinity. Y of 2 is undefined. And then we said that the further we get from 2, and what's interesting, right, is that we actually can't have s less than 2. The further we get from 2, we said the Laplace transform should get smaller. We know exactly what this function looks like. This is the reciprocal function shifted right 2 units. And we're only looking at the domain of s is bigger than 2. So yes, you can see, right, if this is our s-axis and this is our y-axis, you can see the Laplace transform does get smaller the further we are from 2. So we did exactly what we wanted to do. And we can see that, yeah, the closer s is to 2, the bigger the Laplace transform. We're comparing how similar our function is with e to the st. Okay, so that's what we have right here. Now, you might be wondering and saying, Jason, what the heck does this have to do with ODEs? You promised us, Jason. You promised us that we're going to turn derivatives into algebra, but so far we haven't done any of that. So far we've just done some sort of nonsense. Well, don't worry. We're going to get there. Remember, we are going to turn derivatives into algebra. We already are transforming our independent variable from t into s. We're going to use that in a couple videos from now, after doing some more practice. We will use this to solve differential equations, okay? And it will eventually lead us to deal with discontinuous forcing functions as well. We're going to end this video, though. Going to do what we can when we can. We're going to end this video by introducing some shorthand. So yes, the Laplace transform is a function. You know, again, there's like a hidden subscript for what function we're applying the Laplace transform to. Really, there's like infinitely many Laplace transforms depending on what function we are, but it's going to be a function of s. It's going to be a single variable function of s. And what we often end up doing is we actually kind of switch what we focus on. And we write it like this, with brackets, with a script L. Okay, a cursive L, and we say, all right, this is really the focus here. And this is a function of s, but we don't really quite write it as a function of s. It's a bit of sloppy notation. And then what we would say for our function is that our Laplace function that we found for our specific y was s minus 2, as long as s is bigger than 2. So this is how we would really write what we found in the last example. Okay, then the final disclaimer before we end the video is something I said verbally, but the Laplace transform on a function only exists if y doesn't grow too fast. If y grows too fast, it won't exist for any s. So if y grows no faster than an exponential. Okay, and what that really means is that there is some real number m that has the property y, which is a function of t, is bounded by e to the mt for eventually. Okay, for t big enough. So that's not that important. What you need to know is that we are requiring for the Laplace transform to exist, that y is not growing faster than an exponential function. This is a more precise mathematical definition of that. Not super precise, but a little bit more precise. And that's basically it for this video. We have more practice finding Laplace functions in the next video. And then I'm also going to tell you that we don't need to find it every time. We're just going to write some common ones down and use them from a table to save ourselves some time. Okay, so we have that coming up, and we'll eventually use them to solve differential equations as well. Let me know if you have any questions, and have a good one.